Hi, my name is Ken Johnson. We're here at APEC in San Antonio 2018, and we're here to just do a quick walkthrough of our booth and show you the equipment we have. So what we're going to start is over here. We're going to look at our WaveSurfer 3000. This is just a really nice basic oscilloscope. It goes up to 500 megahertz, and we're just looking at some serial decodes on this. This is a great basic lab scope, and we sell a lot of this. It's a really nice little scope. If we move over here to our left, we've got the HDO 9000. This is a 10-bit 4 gigahertz oscilloscope. We're using this with our power rail probe, the RP4030. And what we're doing here is just a quick compare of the power rail probe to a 10x passive probe. We're looking at the same line on both. That's the same signal for both. You can see the power rail probe is a nominal 1x attenuation, so the noise value is very low. It's also very quiet. The 10x probe picks up a lot of interference in EMI just due to the ground loop on the probe, which is not ideal, whereas the power rail probe can plug right in to a MCX or U.FL connector or something like that. Really minimize your noise, so you can see the power rail probe in the top is really superior to a 10x probe, looking at a low voltage rail for just about every reason. If we move over here, we've got a wide variety of our probes. This is our high voltage differential probe product line. It's our HVD series. This one is a 6 kV differential probe, 6 kV common mode. It has a 7.6 kV voltage swing, and it's really the best probe. And that we also have a probe like this, rated 2 kV, which is great for 1500 volt DC buses for solar PV inverters or welding equipment or UPS systems. And this is the workhorse at 1 kV, which is very common for 600 volt class or 240 volt class products where you have a 1000 volt or a 500 volt DC bus. These probes, all of them, are 1% DC gain accuracy, 65 dB CMRR at 1 megahertz, and very, very high offset capability. So very unique. It's really a very unique probe in the industry. This is our high voltage fiber optic probe. It's called the HVFO 103. This is rated for 60 megahertz. It's fiber optically isolated, so it has a nominal 35 kV fiber optic isolation to ground. This is the transmitter. Optically, it transmits out. There's a tip that'll measure the small signal riding on top of a floating high voltage signal. It transmits that fiber optically. This is battery powered, so that's why it can be that high up above ground. This is a fiber optic link right here that can be purchased in tens of meters of length if necessary. And then this is the demodulator, optical to electrical demodulator. That goes to the input of the scope and displays the signal on the scope. This oscilloscope here is our HDO 6000. It's a 1 gigahertz, 12-bit, high-definition, high-resolution oscilloscope based on our HD 4096 technology. What we're looking at here is a conduction loss test, switching loss test of a MOSFET in a flyback power supply. As we move over here, this is our 8-channel 12-bit scope. It's the big brother of the one we just saw. It's double the number of channels, the same 12-bit performance. It has up to 1 gigahertz of bandwidth. What we're looking at here is we're looking at 5 different power rails plus a current in orange, and we're looking at a PWM gate drive signal, which is really being used as our digital clock. From that digital clock, we're extracting a period. Over that period, we are calculating various quantities for all these different rails and the current, and we're calculating things like the RMS, standard deviation, the mean, the worst case peak, the worst case peak positive and negative, peak to peak, etc. We can then look at that. If I touch that there, you see that's purple. That's that 699.994 mean value for the 700 millivolt rail, as I expect, but there is some variation of that rail over time, and we plot that variation over all those individual per period measurements right here. So that is not a captured waveform, that is a calculated waveform that helps bring out the behavior of something that's changing, but it's very difficult to see what the change is without this type of program. Lastly, what we have here is our motor drive analyzer. This is our 8-channel 12-bit. It's built on the platform we just saw, so it's still an oscilloscope, but it also has 3-phase electrical and mechanical power measurement capabilities. So if I look at this right here, if I look at the setup, this basically gives me the ability to look at the whole flow through a motor drive from the AC input to the mechanical output. Right now I'm just looking at the drive output. I'm looking at a 3-phase, 3-wire configuration. These are my 3 voltage and current signals right here. If I expand that out, I can see what looks to be PWM and my AC, my drive output current. This is a very long acquisition, so I'm capturing 2 seconds of data, and I'm looking at this entire acquisition, but I'm using the zoom and gate mode. That zoom and gate mode allows me to zoom in on one part of that full acquisition. Now these calculated mean power quantities are only for the zoomed area right here. Then I can touch these cells, just like in that last program, and I can see what these power quantities over time are. So for instance, power for the three-phase value, the nominal mean value here is 1.362 volts, but it's changing a lot. As my load collapses, I can see the power goes down, both the reactive power in magenta and the real power in blue, but I can also see some interesting behaviors in my power factor. My system seems unstable in such a load collapse. The power factor goes from 1 down to almost -1, recovers, and it oscillates back and forth. So it really tells me something very important about the stability of my system. We're not showing it here, but we have a lot of different ways to measure speed and torque. Pretty much if you have it on your bench, we can find a way to measure it, and the same thing for torque. In addition, we can calculate torque from a known motor torque constant and a measured current. So you can basically get torque and speed at your bench without needing a dyno, and an R&D engineer can do a lot of very functional good checks on mechanical power without having any special sensors or equipment. So Alex, that's going to about wrap it up. So thanks for your time, and we appreciate you spending time with us at APEC in San Antonio.